Today I want to talk about fins, and I want to show you how they're really not that scary. What are fins? Fins are heat dissipating elements that increase the surface area of whatever you want to cool down. In this case, from the drawing, you want to cool down steam flowing through a pipe, and you're using a fin that expands, that increases that surface area of the pipe to cool it down. So fins are usually used in circuits, in chips and whatnot. They have plenty of applications, and they are very important in heat and mass transfer. So to better understand fins, I have a problem. I will give you 2 minutes to pause the video and read the problem statement. Okay, so now I assumed you paused it, and now the first step to solving the problem is to list the things that we know. So one, oops, one known. Okay, what do we know about the problem? We know the dimensions of the fin. We know the surrounding air properties, so the temperature of the surrounding air and the heat transfer coefficient H. So properties of surrounding air. What else do we know? We know the base temperature, right? The temperature of the pipe. Base temperature. Okay, so these are the things that we know. Also, notice that this base temperature is constant along the pipe. So this problem occurs at steady state, and at steady state the temperatures are constant throughout the whole, so they don't change with respect to time. So that means that the temperature along this pipe will be constant no matter where it is. That means that the temperature is constant here, and it's constant here at the interface with the fin. Okay, so the second step is to list the things that we want to find. What do we want to find in this problem? We want to know the heat rate dissipated by the fin. So heat rate, let's label it QF. But what do we need to find to know the heat rate? We need to know the temperature profile, right? So temperature profile of the fin. So we want to know how the temperature varies along this object here. Remember, Professor Servio usually iterates and repeats and says that if you know the temperature profile, you know everything about the problem. So usually in heat transfer problems, you want to find this temperature profile. This is very important. Okay, now 3 is the assumptions of the problem. What are the assumptions in this problem? So the first one, and perhaps the most obvious one, is steady state. I already mentioned it. So there are no time-dependent properties. Nothing changes with respect to time. So steady state. Okay. What is another assumption? We can assume that radiation is negligible. The temperature of steam, we can assume that is lower than, say, 600 degrees Celsius. At temperatures higher than this is when radiation becomes significant, but in this case it's a fair assumption to neglect it, given that it complicates calculations, and most of the time it's not even its effect is not even significant. So negligible radiation. Okay. What other assumptions do we have? We also can assume that properties don't change with respect to temperature, so they are constant properties. Constant properties. Even though this is not the real case, the thermal conductivity is a function of temperature, depending on the material and whatnot. But for the scope of this course and for the scope of this problem, we will just neglect that variation, that dependence. And then perhaps one of the most subtle ones, and one that will really simplify this problem, is assuming that the fin is thin enough that the temperature only depends on the radial direction. So to better understand this, let me just first write the assumption and then I will draw the axes. So thin, fin, and then it's a 1D problem. Okay, so what do we mean by this? Let us first draw the possible directions of temperature dependence. In this case, we will use cylindrical coordinates because they are the most convenient coordinates to use in this case. As you can see, the fin has a cylindrical shape, so that's why it's the most convenient to use. So this is the axial component, or the z direction. This is the radial direction, so it goes outwards from the center, and this is the angle direction, theta. We need these three coordinates to completely specify any point in the cylindrical coordinate system. So the first thing to consider, can the temperature vary along the angle theta? Well, if you look at this problem, there is symmetry along the angle. As you can see, the temperature of the base is constant along the whole surface, so the temperature will be the same on this ring. That means that heat will just flow with symmetry along the angle. It'll flow equally outwards from every point. So it could flow like this, like this, like this, like this, and so on. Because of this, it wouldn't make sense to say that the temperature depends on the angle component. What about the z component? So before we said that the fin was very thin. It was so thin that we can neglect the temperature gradient that could occur along the axial direction. So that means that the temperature along this, say this line here, is equal to the temperature, say along a line here on the center, and is the same as the temperature on this bottom line here. So that means that temperature, the isotherm, is basically a cross-section of the fin, a complete cross-section. In reality, there is a small thermal gradient along the axial direction. So this center, the central line that I drew, is gonna be a little bit warmer, a little bit hotter than the one on the surface, because this one is more exposed to the ambient air, so it's gonna be cooler. However, if the fin is thin enough, we can neglect this temperature gradient and say that the cross section is basically a complete isotherm. So an isotherm is a complete cross section, like this. This is one isotherm. In other words, any point that has the same radius in the fin will have the same temperature, which makes sense to me. Let's draw another isotherm, say a closer one to the center, and now say let's draw the warmest isotherm of all, which is here on the surface temperature. So I already drew it. Notice that heat always flows perpendicularly to the isotherms. Since heat flows symmetrically radially outwards, the only shape that is always perpendicular to any of these arrows is just a circle. So it makes sense to think that isotherms are circular, or to realize that isotherms are circular. This leads us to the next step, which is setting up the differential control volume. So step number 4, differential control volume. So the trick to drawing a differential control volume is to set two isotherms really close to each other, so close that the only difference between the two isotherms is just an infinitesimal increase along the direction of temperature dependence. So imagine this is that middle isotherm that I drew, and let's draw another one almost on top of it, really next to it, this one. Oh, oops, just redraw that better. Here, and it actually looks kind of like a donut. This, and then like this. Okay, drawing is just so bad. Okay, let's try that again. There we go. All right, you kind of see what I'm saying here. Just imagine these two isotherms just drawn next to each other, and now let's label the dimensions of the isotherm. So we have the axial thickness, the radial thickness, sorry, which is an infinitesimal amount, so dr. And notice that we can have infinite in differential control volumes. You could have drawn a differential control volume really close to the center of the fin, or close to the outer edge, because it's given by an infinitesimal thickness. So you can have as many as you want, and any one of them will completely define the fin as a whole. So from this differential control volume is where we get our our property balance for the system, and from the property balance we will get our temperature distribution. So it's very useful to draw differential control volumes. What about the thickness? Will the thickness be any quantity different from the actual thickness of the fin? Not really, because we said that the temperature doesn't vary along the axial component. So the thickness of the differential control volume will just be the thickness of the fin overall. So this leads us to the next step, which is setting up the energy balance, the differential equation for the system, which comes from an energy balance. So differential equation. Okay, so to set up the differential equation, we have to resort to the holy grail of chemical engineering. It is the general energy or quantity balance that we all learn on our first day of chemical engineering. Usually goes in the form of in minus out plus generation equals accumulation. Okay, so what about this accumulation term? We can definitely cross this out, because we said originally that one of our assumptions was that we didn't have any time dependence. None of the temperature doesn't change with respect to time. There's steady state, so this is equal to 0. What about generation? Does the fin generate? Does it sink any heat? This could be tricky because, as you may recall, we defined fins earlier as heat dissipating elements. We said that they dissipated heat, but that means that all the fin is doing is actually just increasing the surface area of whatever object you're trying to cool down. In this case it's a pipe. You're just increasing the surface area to expose it to have a higher amount of surface area exposed to the surrounding air, which is at a lower temperature than the pipe temperature. So by increasing that surface area, you're just enhancing heat transfer. You're not absorbing any heat transfer on your own. You're not keeping that heat. You're actually just transferring it to the surroundings. So this is equal to 0, and this leaves us with the trivial balance of in minus out equals 0. So we need to first find what are the heat rates coming in and what are the heat rates coming out. So let's start with the conduction heat rates. These are the ones that we just drew here that flow radially outwards. But notice that there is also another type of heat loss, that is the convection heat loss, that occurs between the fin and the surrounding air. But let's first start with the conduction one, which is the the one perpendicular to the isotherm. So we can draw it here as going from the center into the wall. This is Q evaluated at R, and then we also have heat coming out evaluated at r plus the infinitesimal increase dr. Right? So these are the two conduction heat rates of our differential control volume. And what about the convection heat rates? Well, they occur between two media, so the fin and the surrounding air, and they are expressed from Newton's law of cooling. We'll come back to this later, but let's label it first so we can show it as a vertical component. And notice that it's both the top and the bottom surfaces, at which this heat rate occurs. Okay. Also notice that this quantity is a differential quantity. And why is it differential? Because it occurs on a differential area element, which is given by this dr term. Notice that this the inner cross section at which the conduction heat flow occurs is not a differential quantity, because the thickness is it's a finite thickness, it's T, and the inner surface and the surface area, like the inner cross-sectional surface, is also a finite quantity, which is given by 2 pi r, right? So that is why these quantities are not differential, but only this one is differential. And this will be relevant when we want to find expressions for these quantities. But so let's first start with the conduction heat rates. Let's find expressions for these two quantities, Q evaluated at r and Q evaluated at r plus dr. So conduction first. Okay, so how do we evaluate Q evaluated at r? We know we can use Fourier's law. Fourier's law. Fourier's law. What about Q evaluated at r plus dr? We don't really know how to evaluate the function at a different point, right? Like it's gonna be hard. It's hard to define. So because of this, we'll use a very useful, resourceful technique, which is a Taylor series expansion. So let us first define a Taylor series. Let me just erase here, make some space. Okay. So Taylor series. So all a Taylor series allows you to do is to predict or define a function at a point that you don't know based on the characteristics of that function at a point that you know. So the general formula for the Taylor series is the following. You have your dependent function, depends on x, and this is the function that you want to evaluate. This is the thing that you don't know, the new point that you don't know. You basically can define this new point based on the function at a previous point, or at a point that you know. So it's given by a sum of all the differential elements of that function. So it's the function itself. Well, let me just use a different. Okay. So it's y. It's the derivative, the nth derivative of y evaluated at the point that you know. Let's call it x naught here, times the difference between the new point that you don't know minus the original point raised to the power of n divided by a factorial element, n factorial. Okay, this is just a fancy formula of saying if you know the function at a given point x naught, you can find the function x evaluated at a new point x by doing this fancy sum. So this is, we can draw an analogy. Imagine you were a police officer and you were given, you had to predict the position of a suspect based on the position of the suspect at a previous time. So say another police officer was telling you the position of this suspect. Say the suspect could only go on a straight line. Imagine this was the straight line. Okay, imagine this is, let's call this y, I guess. And the suspect could move around this line. And all the police officer was telling you would be the velocity of your suspect and the position. So imagine this is just time and this is y, and you wanted to plot it. So say at time equals 0, the police officer tells you, okay, the suspect is at 2 meters along this line. So imagine this is 2 meters. So this is the initial position of the suspect. So let's draw it here as well. So imagine the suspect is here. And the police officer is also telling you the velocity of the suspect. So he tells you, and the velocity of the suspect is 4 meters per second in the positive direction. So say, 2 meters per second in the positive direction. So imagine this is 1 second. Say this is seconds and this is meters. So he tells you it's 2 meters per second, and you can basically draw that velocity as a vector here. So kind of look like this, right? And so that means that 1 second later your suspect will probably be 4 meters away, right? So this is kind of what you would predict. However, the suspect might also have higher derivative terms. Not only a velocity, but he could also have an acceleration. He could also have a jerk. He could also have a pop. Yeah, I think I forgot the name of the other ones, but you know what I'm saying. The suspect could have higher derivative terms. He could decide to stop at any point. But basically, what you would want to do is to predict the position of the suspect at different times. So how confident will you feel predicting the position of the suspect, say 1 second later, say at this point, 1 second later? You'd probably say, okay, assuming that the suspect only has a constant velocity, you could predict him to be somewhere here, right? 1 second later, somewhere here. And I mean, 1 second later, it could be it's a completely fair assumption, completely fair estimation. What if you wanted to tell where the suspect is at, say, 60 seconds? Well, I guess you would probably say, okay, well, if I extrapolated that line, he could probably be up here somewhere. But you're completely not sure. It's very uncertain because 60 seconds after, the suspect could have stopped, he could have gone back, he could have done many things. So I would be a lot less confident about this prediction than for this prediction. But what if you wanted to predict his position, say, at a fraction of a second, say, somewhere here, say at 0.001 seconds? Then you'd be pretty confident that at 0.001 seconds, he's slightly displaced from his original position, and you would be a lot more confident to predict this position than this position. So here you're kind of using a Taylor series to predict the position or the function at a new point based on the function at a point that you already know. So how can we relate this back to the heat rate and stuff? Well, we can say that we can evaluate Q evaluated at R plus dr. So Q evaluated at R plus dr using this formula. However, same as the case with the suspect, we will only use the first derivative. So in this case it would be the velocity, but since the differential increment is so small, since the displacement here is so small, it's differential, it's infinitesimal, it could be okay to neglect the higher derivative terms. Say neglect the acceleration, the jerk, and the pop, and all of those, because if the time is so small, it doesn't really matter. All you care about is the main component, which is the velocity, the higher derivative terms. And also notice that as your n increases, this denominator increases very fast. So it's definitely okay to just neglect all the higher order terms. So you can write that Q evaluated at R plus dr is just the original function, or the zeroth derivative, which is the original function. q evaluated at r, which you know, plus the first derivative when n equals 1, dq dr evaluated at r times the differential increase, or the difference between the new point and the old point. So r plus dr minus r just gives you dr, right? Dr plus, and you could keep going for n equals 2 and so on, but we'll kind of neglect that just because of how small this is. So just from conduction, we could evaluate what in minus out will be. However, keep in mind that we still need to evaluate the convection term, but for now we'll just evaluate the conduction ones. So we have the in, we just write again in minus out, in minus out equals 0. So in will just be q evaluated at r, q evaluated at r minus out, q evaluated at r plus dr, which is equal to q evaluated at r plus dq dr evaluated at r times dr. Okay, and that would be equal to, you can cancel these two terms out, and that would be equal to minus dq dr evaluated at r times dr. Now, how do we express this quantity here? Well, remember Fourier's law. Fourier's law basically expresses the heat rate from the temperature gradient evaluated at a given point. In this case, it would be evaluated at R times an area element times the conductivity, the thermal conductivity. So let's write that down. Let's keep the derivative term out before. So minus d by dr off. So what is q evaluated at r? Q evaluated at r is given by minus the conductivity times the temperature gradient, right? Here the gradient reduces to a one-dimensional temperature gradient. This is evaluated at r. And what is the area element at which this heat rate occurs? It's this inner surface area. So this inner surface area. And how can we express this inner surface area? Well, a cool trick is just think that you're stretching it as a horizontal wall. So imagine you're just unrolling it from a circle and you're just stretching it. So what is the length of this horizontal wall? It's actually the circumference, right? So it's 2 pi r. And what is the height? Well, it's just a t, the thickness of a fin. So the cross-sectional area for this heat rate is just 2 pi r times t, right? So let's write that down, times 2 pi r times t. So now the negative signs can cancel out, and we said the properties are constant, so the k term can be pulled out of the derivative. This 2 pi and this t are constants as well, but notice this r here. This r is not a constant, so it is actually dependent on r as well. That means that you will have to do the chain rule here. So let me just clean this a little so the negative signs go away. Take out the k, take out the 2 pi, take out the t, and then we would have d by dr times r times dt dr, right? And then chain rule, so you take the derivative of the first times this function plus the derivative of the second times the first. So this is k times 2 pi t multiplies the chain rule. So it's gonna be dt by dr, right? Because the derivative of r is just 1 times the other function, dt by dr, plus this function times the derivative of the second one. So r times d squared t by dr squared. Okay, so this is what the conduction heat rate difference boils down to. It's kind of a simplified way of writing in minus out. Notice here I made a mistake. It shouldn't be equal to 0 because we're still, well, it is equal to 0, but we're still not taking into account the convection heat rates. So that is what we will do right now. So now the convection heat loss. We labeled it like this. And there's also a bottom element here, dq convection. So as I said before, this is the convection heat loss can be expressed from Newton's law of cooling, which has the form of the heat transfer coefficient of the surrounding air, which is a property that depends on the velocity and whatnot of the air, of the surrounding air properties. So it's usually given by, just right down here, dq convection is given by H, the heat transfer coefficient, times the temperature difference of the surface of this surface and the temperature of the surrounding air, which is constant. So notice that this temperature in here, this have slightly different radius. So if I were to draw a line here, Jesus, like this. If I were to draw here, this line has a different radius from this green line and from the gray line. That means that the temperature is actually not a fixed temperature, it's actually evaluated at any R value in between. So that's why we take T evaluated at R minus T infinity. This is the temperature of the surrounding air outside of the boundary layer. And you have to multiply this value by the differential area element, the AS. Let's call it surface area. So what is the surface area in this case? It's actually the surface, the top and the bottom surfaces. So this top surface here, top surface, and the bottom surface as well. So how can you express this area? It's actually the difference between two circles, right? So we could write it as T of R minus T infinity times, so it's going to be pi R squared, right, of the outer, pi R squared of the outer circle minus pi R squared of the inner circle. So it's going to be pi times R plus the R, this squared, minus R squared, right? So same thing, times pi. And then here, when we expand this, we have the two R terms that go to 0, and then we'll also have dr that will be squared. So a similar analogy to what we did last time, we truncated all the higher differential terms. Because dr is already small, imagine how small dr squared will be. So because of that, we can neglect that R squared minus R squared, they cancel out, and this dr squared cancels out, and we are left with 2 pi R, right, dr from the expansion of this. Also, notice I just realized that it's the top and the bottom surfaces. So this is actually multiplied by a factor of 2 here, because it occurs in both surfaces. So instead of a 2, it should be a 4. Here, it should be a 4. Just realized also that I wrote pi twice. Okay, so this is the way that we would express the convection heat loss. So now we can put everything together. We can go back to, we can write our conduction and convection heat rates. So let's do it here on the side. In minus out equals 0. Okay, so now we can put the convection and the conduction heat rates together. So from the previous tab, I won't go back to it, but you might recall from your notes. However, I think I made a mistake. Actually, I forgot a dr term, so I'll just show it to you. 1 second. So yeah, sorry for the mess, but it's down here. So remember there was a dr term coming out from the Taylor series expansion? I think I forgot it when I first wrote the video. I just added it here, so there should be a dr term multiplying this whole thing. So this should be times dr and times dr. So sorry about that. But now here I'm gonna add it. So the final form of the differential equation is gonna be the conduction term minus the conduction term and the convection term. So from the conduction term we have k times 2 pi t times dt by dr plus r d squared t by dr squared times dr. This is the dr I was talking about, minus the convection one, which is 4 pi r h t of r minus t infinity times dr. So I noticed about my mistake because I noticed, well, it's always necessary for you to have dr terms that cancel out. It's never okay for you to have a random differential element in your final differential equation. You should only have derivatives. So this is a good indication that you're doing things right, that you have dr terms that you can cancel out. And also notice that this are evaluated at r. Okay, so that means that we can cancel these one out. This is equal to 0. And so let's write down our final differential equation by putting some of the constants together. We can divide by 2 pi. We can also divide by k by t. We can also divide by r to get rid of the r on this side. And that will leave us with this equation. So it's going to be, by dividing by all that I told you, it's going to be d squared t by dr squared plus 1 over r times dt over dr. This is all evaluated at r, minus 2h over kt times t r minus t infinity equals 0. Okay, so this is almost quite finished, but we can simplify it a little bit more. You may notice that this equation here is non-homogeneous, so there is a constant term that could complicate our computation. That would increase our computations. So we want to minimize computations as much as possible. We want to make this look as neat as possible, as homogeneous as possible. So what we will do is that we will create a new variable, call it theta, that will just be these two things together, t minus t infinity, t of r minus t infinity. Why is this so convenient? Because t infinity is a constant value. So whenever you want to take the derivative of theta, it's just going to be the same as the derivative of the temperature, because of the constant characteristic of t infinity. This is just equal to t of r. So that's perfect. We can easily replace that function here, and that will give us the final differential equation, which has the following. I'm gonna create a new layer, which has the following form. So 1 second. Okay, so the final differential equation is basically d squared theta divided by dr squared plus 1 over r d theta dr minus, so it's actually 2h over kt times theta equals 0. We can even simplify it further by calling this group of constants m squared. So we have m squared equals 2h over kt. Okay, so if we do that, let's write it down again quickly. dr squared plus 1 over r d theta Okay, so this is a solvable ODE, but first we need to specify our our boundary conditions. You know that for an ODE you need as many boundary conditions as the order of your ODE. So here the order of these of this differential equation is the second order differential equation, which means that we need two boundary conditions. The boundary conditions are evaluated at the endpoints of your temperature, of the direction of your temperature dependence. The two endpoints here are at the inner radius, so here at this isotherm, and are also at the edge, so here. Here's where you will evaluate your boundary conditions. So let's start with the easiest one here at the center, at the surface of the pipe. We said earlier from the problem statement that this had a constant temperature, that the pipe had a constant temperature TB. So that means it's here, boundary conditions. So at R equals Ri, the inner radius, T equals TB, right? T of R, T of Ri equals TB. However, we did a change of variables, so we have to express this in terms of theta. So we can just say theta evaluated at Ri is just going to be equal to TB minus T infinity, which is equal to theta B, right? Theta at the base. And then what about at RO, at the outer radius on this outer surface? R equals RO. What about here? We have two options actually. We might say that there is some heat loss due to convection at this outer surface. There is some heat that is flowing outwards radially like this. So that is one possibility. Let's write it down. The way that you would express it is basically from comparing the conduction heat loss with the convection heat loss. At this point, since it's at the edge of the fin, the conduction heat loss is equal to the convection heat loss. So let me just write it down. Conduction at RO is going to be equal to convection at RO. How do we express the conduction at RO? It's going to be minus K times the temperature gradient evaluated at RO times an area term. But notice that the convection area is just the same, so they will cancel out. So we can do a flux balance. So it's going to be equal to minus K, yeah? And then this one will be equal to H times T of RO minus T infinity times the area term that will cancel out. Anyway, we have to transform it to the theta variable. So, and we can also isolate our derivative term. So that will give us dt by, well, actually I said that we would replace here. Just replace theta. Theta RO is just going to be equal to minus H over K times theta at RO. So this is our way to express heat loss due to convection at the outer edge. And then the other way that we could express it is actually from our assumption. We assume that the fin was very thin, so thin that it's not likely for heat to flow out of this surface because it's a very small surface, it's a very small area. So compared to the upper and lower surfaces, it's not likely that heat will flow outwards from here. It'll probably flow outwards like to the top or to the bottom. So we can say that on the outer edge, the surface is adiabatic. So to express it mathematically, we would just say that the conduction heat loss is equal to 0. So this is equal to 0. These are two boundary conditions. And to be able to completely solve the problem, we need to find the solution of this differential equation that we wrote down. So the way that you normally would solve these type of differential equations is by starting by doing infinite sums, solutions that have the form of infinite sums. And Professor Servio has actually a formula sheet where he has the solution to all of the differential equations that you will encounter in this course. However, you have to be very careful to choose the right one, including the sign. So this sign is very particular. The solution depends on the sign. It also depends on this coefficient. It depends on this radius term. So the solution for this ODE in particular is actually a modified Bessel equation. It has the following form. The following form is theta will be equal to I valued at m r c1 plus c2 k. These are modified Bessel functions of order 0. They behave similarly to trig functions. You don't really need to know exactly how they behave nor how they look, but just know that they're sort of cyclical as well as the trig functions, and they have specific properties. So when you evaluate them at 0, some of them go to 0, some of them go to complex infinity. I think Professor Servio will go over this in class. You should probably have a table for all of these properties because they are not in the formula sheet. So keep that in mind. But for now, we won't really encounter any of those problems because we will evaluate our function at Ri. Ri is the smallest value, the inner radius, and it's not equal to 0, and Ro, or the outer radius, which is not equal to 0 either. So this is the form of our solution, and then we also want to evaluate the derivative, first derivative. So it's going to be equal to c1 I1 minus c2 k1. Notice that this mr and this mr, this is the same, this is the square root of this m squared, and this is just the value at which the function, the Bessel function, is evaluated at. This doesn't mean that I'm multiplying it or anything like that. Anyway, here we have our solution, and we have the two differential equations that we could have chosen. We could have chosen the heat laws or the adiabatic surface, and at the inner surface that we have a constant temperature. This is set, but here we could have chosen. Of course, this solution here has the constants, the integration constants C1 and C2 are a lot more complicated, so I won't really write it down here. I'll write down the solutions for this boundary condition. So the final solution for this problem is theta divided by theta b, the base temperature, is equal to Bessel function order 0 evaluated at mr. Just write it down. And all you have to do for this is just algebra. It's not too bad. It's actually the solution for this. You can find it on page 167 of the Heat and Mass book, which is Fundamentals of Heat and Mass Transfer. It's the 7th edition, so it's a good reference, a good source. Okay. Okay, it didn't fit, but anyway. This is the final solution for the temperature profile. And now, to find the heat rate, you basically have different ways. So the heat rate is basically why we are solving this problem, why we are solving for the temperature profile originally. The heat rate is kind of what you're looking for. So there are multiple ways that you can evaluate the heat rate. Perhaps the simplest one is just evaluating the heat rate that occurs here at the inner surface. So all the heat that crosses this inner surface has to be the total heat dissipated by the fin. You can express it as the conduction heat rate. So you can express it as, let me just express it as QF is going to be equal to minus K times d theta by dr evaluated at Ri times the inner times the surface area of this inner cross section, which is given by 2 pi Ri times T. Remember the vertical wall, the horizontal wall that I told you about? Here the wall would be unrolling this inner ring, this inner radius. So this is one way of expressing the heat rate, and another way is by integrating the heat rate that occurs, the convection heat rate occurring throughout the whole surface area of the fin, also including the outer surface. It depends on what boundary condition you used, but you can also express it as an integral. So the way that you would express it is as follows. So you can just say times the integral along the surface, let's call it the total surface because it's a surface area, top and bottom, plus the side times plus the edge surface area of the convection heat loss. So it's going to be T of R, because it only depends on R, minus T infinity times dAs. Here you can replace this with theta, and it's equally valid. And you can also express it as the conduction. Actually, these are the main two ways of expressing it. I feel like there's probably another one. If you find the other way, just post it in the comments or let me know. I think there's probably another way of finding the total heat rate. But anyway, we have reached the end of this video. It was a very thorough video, I guess. I wanted to explain things with as much detail as possible because I felt that when I was doing this course, many things were just left unsaid. So please let me know if everything was clear. Please post comments if you have any questions. And thank you for watching.